Okay, let's try a function which doesn't behave as nicely, and guess that doesn't work too well. So the function is x cubed minus x plus 1. Very simple. Its derivative is 3x squared minus 1. And let's start at a starting value of minus 0.5. Do Newton, check guess. Do Newton again, check guess. So again, zoomed out. Now we're zooming kind of back in. And let's just see if we can look at what the function looks like. So again, we're coming in. That's all good. So we are approaching the 0 over here, but are we really going to reach it? So here we are. And notice what's happening. We've sort of zoomed in on this minimum here, right? And the next step, you don't want to be at a minimum. You get zoomed all the way out. And we've really made it nowhere. Let's just see what happens again. Again, we're coming back in. Coming back in. Coming back in. And so this time we actually made it to the other side. And perhaps we'll just we will be able to make it. So we did find the root. It took 20 steps. Now that was starting here. Let's try to start somewhere more into the danger zone. Oops. Sorry about that. See, if you get it just right, I probably haven't done that, but you can sort of see that it's kind of bouncing back and forth. Now here we might just see, when you get too close to the minimum, anything can happen because you get very long distances and then you sort of break out of the cycle. So let's not do that. Let's just get away from that for a moment. So, and again, once you get out that far, you'll probably end up at the root because it'll come back in and that'll be that. But the idea is you can get trapped in this sort of valley, and as you go back and forth, if you just happen to be unlucky, you might get trapped in there. Otherwise, you might get sort of shot out to infinity or minus infinity. when you reach one of these points, and then you're sort of broken out of the trap. So that's stuff that's going to happen with Newton's method. It's a good thing to try a variety of starting points to monitor your progress with Newton's method, to make sure that, you know, this isn't happening. It shouldn't take that many steps to get it to start converging. So if you don't get convergence pretty quickly, take a new guess. All right. So notice how it sort of wiggles, and we are sliding along the function. Do you notice we're getting farther and farther away from the origin? And basically, if you graph sine 1 over x, or just think about it, what you have is a 0 at infinity, and that's what we're actually zooming in on. So we're just going to keep going farther and farther out. Notice how it's roughly doubling each time. 2, 4, 8, 16, sort of 32, roughly. $67. This is more like 34, 68. So that's kind of nice. That's actually showing the doubling of that. Now let's look at if we were to use the secant method. So first of all, we need a second point. So we'll just use Newton for that. Now let's try the secant method. So instead of 8, it's 6.3, kind of 1.5 times previous value. 1.5 times 6 is pretty good, close to 10. And so you can see that it's actually, the secant method is indeed slower than Newton's method. What if we actually did the numerical Newton's method? Let's initialize that again. And it does indeed look like it's doing the doubling. So, numerical version of Newton is working just fine. Back to sine 1 over x. Alright, so you can see here that what we were doing before, we're basically following this downhill slope out to infinity. So let's try to get past that little slope there. We just do that with this, and now we try to use Newton's method. Check the guess. Whoa. Notice every time that we're sort of shifting the view of this thing, it's a little slow. And that's because of this whole sine 1 over x near 0 thing. It's trying to do some computations that take a long time. And now we have a root. And we converge, and we're all happy about that. And there you go. Now, this is just one root out of many, infinitely many near zero, in fact. And so if you wanted to, you could find more and more zeros. It'd be pretty hard to really converge on particular ones as you go in, because they're all so close to each other. Numerically, it's just pretty hard. Analytically, it's actually easy, of course, because it's just, you know, 1 over wherever sine has zeros. So that's kind of nice. Okay. Well, we hope you have enjoyed this little exploration to Newton's method, and we'll see you again next time.